Hello everyone, welcome to today's class, Organic Spectroscopy Analysis. Raman spectroscopy is named after Sir C.V. Raman, who won the Nobel Prize in Physics in 1930. Raman spectroscopy is a spectroscopic technique used to study vibrational, rotational, and other low-frequency modes in the system. Raman scattering is an inelastic scattering effect. The scattered light has different wavelengths as the incident light. Raman and infrared spectra of a given species often resemble one another quite closely. There are, however, enough differences to make the techniques complementary rather than competitive. In previous lecture, we have studied the selection rule of IR spectroscopy. For Raman spectroscopy, the selection rule states that in order for the photon to be absorbed, the molecule must undergo a change in polarizability. As for infrared, change in permanent dipole moment, and for Raman, the change in polarizability. For molecules with a center of symmetry, if the vibration is related to the center of symmetry, the infrared spectrum is invisible and the Raman spectrum is visible. If the vibration is not related to center of symmetry, the infrared spectrum is visible and the Raman spectrum is invisible. If the vibration involves both the change of dipole moment and the change of polarizability, the vibration band will appear simultaneously in the infrared and the Raman spectra. If the band in the infrared spectrum is strong, the corresponding band of Raman spectrum is weaker than vice versa. What are the advantages and disadvantages of Raman? First of all, water does not cause interference. In addition, glass or quartz cells can be employed, thus avoiding the inconvenience of working with sodium chloride. Due to the low intensity of the signals, Raman spectroscopy was not widely used until laser became available in the 1960s. A second deterrent to the general use of Raman spectroscopy was interfered by fluorescence. This problem has by now been largely overcome by the use of near-infrared laser sources. As for the applications of Raman spectroscopy, Raman spectra yield more information about certain types of organic compounds than do their infrared counterparts. Raman spectrum on graphene edge showing the main Raman features, the D, G, and G' bands. There are Raman spectra of bulk graphite. 1. A vacuum filtered film with a laser spot focused on a large flake. 2. A vacuum filtered film with a laser spot focused on a small flake. 3. A large bilayer. And 4. Reproduced from a reference. Raman can be used for the analysis of inorganic species. The vibrational energies of metal ligand bonds are generally in the range of 100 to 700 centimeter reciprocal, a region of the infrared that is experimentally difficult to study. These vibrations are frequently Raman active, and scattering peaks are readily observable. Raman can be used for the analysis of biological applications. The advantages of this technique include the small sample requirement, the minimum sensitivity towards interference by water, the spectral detail, and the conformational and environmental sensitivity. Surface-enhanced Raman spectroscopy is a surface-sensitive technique that enhances Raman scattering by molecules absorbed on rough metal surfaces. The enhancement factor can be as much as 10 to 10th power to 10 to 11th power, which means that the technique may detect single molecules. So in this lecture, we have learned Raman spectroscopy and compared it with infrared spectroscopy regarding the selection rules and applications. Thank you for watching.